Welcome to the nominal start of the semester. Here at Bristol today, we've got Dr. Venkatessh Ramakrishnan, who is visiting me to work on some new STAR proposals this week. Venki for short. He got his PhD in 2016 from Aalto University, right in Finland, working in radio observations of active galactic nuclei and blazars. And then he went on to working in Chile, where he became part of the Event Horizon telescope team. Unlike myself, I think he's actually a crucial part of the Event Horizon telescope team, one of the leaders in the radio observation portion of Event Horizon telescope. He's recently gone back to Finland, to Aalto, to continue his work on radio observations of blazars and also branching out into more multi-wavelength, and we'll hear about that today. So Venki, why don't you take off? And if anyone's got questions, feel free to put it in chat.
Well, I think I'm going to be sitting the rest of the day, so yeah, that's okay. All right, thanks, Mike. First, let me assume everyone can hear me well. If not, please let me know. I'll try to make some adjustments. Okay. All right, so let me just get started. So yeah, as Mike said, I'm one of the AGN working group coordinators in the Event Horizon Telescope Consortium. I'm sure most of you might have seen these results on the black holes that was published about 3 years now, and more results are anticipated in the coming months and years to come. It was just mere scratch on the surface. It's going to be we're going to be talking about more. Again, as Mike said about my journey, it's pretty much similar to what we might have as my radio interferometric long baseline network. So my career has also been in such a case. I've gone around all parts of the world for my career. Now I'm back in Finland, but of course having a lot of multi-wavelength partners, with Mike being one of the major partner here, helping me out with a lot of X-ray facilities and so on. I'll get you talk to you more about that. But first, the idea of this project that I'm trying to lead within the ngEHT is that trying to have an atlas of black hole images in the future. I'm sure this is something that would have struck everyone once ngEHT published the first results of the black hole. The idea is to get this going of as many objects as possible. We hope that we could start getting such interesting results in the coming years. But now I'm just going to tell you all the roadmap, what work efforts are being put in order to make this happen. So yes, one of the first objectives here is to image the innermost regions of the black holes, or even possible the photon orbit. And of course, we got the shadow of the black hole. It's published on M87, giving us a big motivation for this feasibility of extending it to as many other sources in the nearby universe. But of course, once we expand the ngEHT array, we'll hope to see far more objects and so on. Then, of course, the accretion flows a bit going on a larger scale than shadow. Obviously, there are far more sources where we will be very challenging to resolve the shadow. So in which case, we can at least study the nuclear regions of these are disk-dominated galaxies which are not actively powered by relativistic jets and etc. And of course, final important objective is the study of jets itself, which is a very important question. Adds a lot of puzzles to simulations and other things. It's going to be very interesting to study the formation of jets, for example, with EHT, because EHT is going to be, the resolution offered by EHT is going to probably give us a deeper view into the base of the jet. Two of the results that we have already published are on 3C279 and Centaurus A. Again, I assume you guys have seen the result. I forgot to include those images here, but at least images have given us have told us what EHT, the capabilities of EHT can show us in greater details about the formation of jets and etc. But again, there are various aspects that still needs to be explored. One of them, of course, being how the time variability of those images, what they really tell us in terms of the formation, collimation mechanisms, and so on. So these three are the major objectives, of course, but it has a much grander design. And the major motivation for this, of course, comes in terms of the EHT array itself. But it's not only the EHT array, there is also more than a decade old interferometric network called Global Millimeter VLBI Array in yellow labels here. GMBA array, otherwise the Global Millimeter VLBI, does observations at 86 gigahertz or 3 millimeter. They primarily consist of networks like the VLBA here in the US, Green Bank, and a couple of stations in Europe, in Spanish Sierra Nevada, and in Effelsberg, Germany, and also a couple of them in Chile. So, of course, unlike the EHT, it doesn't span all across the world, but still at least the resolution offered by GMBA is still sufficient enough to probe the base of the jet, at least in some of the nearby sources. And being at low frequencies, at least we'll be able to see much more sources, again, probably in a nearby universe, and certainly all the powerful radio loud active galaxies. So GMBA is not something new, because it has been publishing interesting results for a long while now. But GMBA was certainly one of the key factors that helped us in developing the techniques for the EHT. GMBA was the test bed for that. So all the instrumentation that went into making EHT a success was already tested out with GMBA, because EHT itself was sort of developed for more than a decade, with several test observations back in 2013, starting perhaps around 2009. But one of the major factors that helped EHT, and the reason why we made a more official release of the image in 2019, is because only in 2017 observations, which was what saw us M87 result, included interferometers like SMA and ALMA. This is important because only then will the sensitivity of the array be sufficient in order to image all the results that we have seen so far. The reason also being that SMA and ALMA by themselves being interferometers, there's a technique in interferometry where you phase up the signals at first at these local sites before the signals are put together as a whole EHT interferometer. This technique called phasing up is one of the major factors for the EHT. Again, this is not new. It has been done for decades with when VLA takes part of VLBA observations. eMerlin in UK takes part of the EVN, European VLBI network, or ATCA in the south in Australia takes part of the LBA observations. But all these observations, when they were done, they were at centimeter wavelengths. Only this was the first time that this technique has been experimented at millimeter wavelengths at these frequencies. But phasing up is not as much of a challenge it is. but at least the important factor is the sensitivity that this technique offers is very important for all these observations. Hence, also the reason why it has been very important for us to really plan and commission the time in the year when all these facilities can observe together. So what ALMA offered us and SMA, and starting 2018, also the NOEMA, which is a successor of the IRAN PTBI millimeter interferometer in, again, French Alps. All these three interferometers have significantly amplified the signals of EHT. And starting this year, starting this March observations, we are also going to have a new technique called passive phasing. Again, as the name goes, passive phasing is going to allow us to detect even fainter objects. So until last year, there was sort of a loose constraint that we can only image sources as bright as, well, or as faint as 500 millijanskis in radio flux. But starting this March, we expect to go further down to perhaps around 50 to 100 millijanskis. This is a big step. This is going to open up a lot of sources. Again, something what I'm trying to do as part of the EHT, and something what we are also doing with Mike in terms of multi-wavelength observations, etc. One key aspect here to remember is to also remember why this is a challenge in terms of doing the observations is in all these low, while observing this less faint sources, less bright sources, it's important to have the calibrators as close as possible so that one can switch between the target and the calibrator. Again, a technique which has been done for decades. But trying to find these calibrators nearby the source, and it has to be at a really close range, is very important. So again, this process is going to take a couple of years. Needs to be a lot of iterations done. But at least the good news is starting this year, we are going to make the first step towards observing more fainter sources in the local universe. And talking about these sources, again, the reason why I've been trying to impart the importance of these sources is that,
So on your method you had before, so you're saying that to do the local phase calibration, you can only do it with ALMA and SMA, or are there other arrays inside the EHT network that do it?
The phasing up thing, well, the phasing up has to be done. Every local interferometer has to be done. And SMA and ALMA for 2017, these two are the only interferometers. And 2018 onwards, we also have NOEMA taking part. So, I mean, it's not something, it is done sort of on the fly during the observations. But yes, they need to be done so that they, okay, let me put this way. So ALMA having, for example, consisting of 40 antennas that take part in our observations. Once you phase up, then they act as like an 80-meter antenna. So yeah, this has to be done, and this is done on the fly. Yeah.
Yes, I guess my question was for the stations on the EHT that are farther east. Like, aren't they going to be observing the source at some point when ALMA is still not, when the source is not visible with ALMA, or to rephrase the question, is already the EHT network as wide as it can get, or you can get farther?
Okay. Okay. So this comes to the important point of how any long baseline interferometer array is designed. How do you design to place the site? How do you pick the site? The important thing is, maybe I could go back here, is you need to have, again, since interferometer works at least as a baseline, so you need to have a mutual visibility of the source. So yes, you are right, but in that case, the way you can perceive the notion is, let's say, and this happens, and this is something we have to always keep in mind. It's a good question you raised. So if, let's say, ALMA, for example, is busy trying to phase up, and you can, when you look into the, I should start having these plots for further talks. You can actually see a particular scan when ALMA is having this phasing up process. It is an outlier. You need to flag those scans. But of course, during that particular moment, other telescopes will be functioning. But again, at least in that instance, we have a baseline for other baselines which are functioning normally. So even if that particular scan we lose of ALMA, we are still going to be observing with, for example, the eastern networks and, for example, the south pole and so on. So it's not a major loss criterion. Again, the reason why we sort of keep iterating over a long time. And also the reason why we have, when we decide the place, we have to decide that there are at least two. But to make it better, again, this has been like a age-old technique from 1950s, 60s, closure relations, where you try to have three telescopes instead of two. Again, something that also benefits VLTI, for example, is that when you have three antennas, you can form a closure network. And what the main advantage of this technique is, any phase errors, which is actually very key factor for interferometric observations, they cancel out when you add the signals from three networks, three baselines. So yeah, so basically, as long as we have three other sites observing the source, when, for example, ALMA is phasing up, it's nothing. We can, let's say, we can interpolate the information, for example. And this phasing up is a very quick process. It takes perhaps like 5-6 seconds or something like that, which is not, we won't be losing it. And of course, this has to be done over the course of the observation, but we won't be losing much information there because other sites will be equally observing. Again, this also goes into how we schedule the observations. Maybe like, if you look more closely, we could have started the observations at a time when the source is already visible for the eastern networks. But again, we try to have this option of having three stations mutually seeing the source. So yeah.
Thanks.
All right. So yeah. So the role of these connected interferometers like ALMA, SMA, and NOEMA are so important that they amplify the strength. And this new technique of passive phasing, as I said, is opening doors to much fainter and nearby sources. So about these sources, at least that we are starting to focus in terms of future observations, is everything starts off by trying to get the massive black hole, sources with quite heavy black hole masses. And of course, these could be sporadically located around the universe. But there is a very straightforward relation of the mass and the distance to the source, meaning that all sources that are closer has a much larger photon ring, which is at least in this table shown by the ring micro arc second column here. So all sources that are closer are going to be having this higher ring size, but that's not alone the important factor, because a source can still be massive but maybe faint at your observing frequencies. So which is why, for example, if you look into the columns that's more towards the end, you see that at least millijansky levels, you can hardly see these sources. And when you look at the corresponding frequencies, some of them are at 1 millimeter, but they are like far too low. For example, NGC 1600 is one of the popular targets, which was reported to have a 17 billion solar mass. about factor of 3 more than M87, studied using stellar dynamics measurements, which is one of the understood to be one of the high precision measurement. But at least at ALMA frequencies, when we did the observations, although ALMA being more sensitive, etc., the flux limit that we saw was almost towards the noise limit of the observations. We are trying to investigate why this is the case. The spectrum is going to tell us more if it is steep and perhaps rising at a much later frequency.
Yeah. Can you remind us the size of the ring and the radio flux for M87 to get a feeling for how much more this is?
The next plot.
Okay.
Okay, so that brings me to this plot of putting together, of course, figures talk better. Something that's more, something that can more relate us to this study is trying to make a plot of the brightness of the source shown in the y-axis here, and brightness, of course, more at 230 gigahertz, the observing frequency of EHT versus the ring size, the photon ring size. So at least we think that the x-axis, the ring size, can be given the mass of the source, and like I said, the distance. This could be loosely around the right value with a precision uncertainty of let's say 10 to 20%. But this is not the main factor for us right now. The main factor is the brightness. And so one of the important things in interferometry is there are when it comes to the brightness, two parameters that are used. One, the total flux, and the other thing is the correlated flux. Total flux is basically the flux seen by a single dish telescope or the dish, for example, like the flux reported by just ALMA in the entire EHT array versus correlated flux is what the resolved flux of the core that we get after correlating the observations and so on. This could be, in principle, this could be the high resolution flux that you get from the observations. Now here, I mean, since EHT is just starting observations, we are far from reporting the correlated flux, which is what is needed when you want to plan a VLBI observation. But at least the expected 230 gigahertz total flux from SMA and ALMA observations are shown here. For some of the sources which are already, like the sources in red are popular targets, which are also part of many calibrator observations and so on. And so is the dark blue sources. The cyan ones, we sort of extrapolated it, assuming a spectral index. This is also something we are trying to populate more and more in the coming months to years time. But what this also tells us is, so we have these three vertical lines here. The black line is the current resolution of the EHT when it comes to resolving the photon rings, the shadow. So anything to the right of the line, theoretically, we should be able to resolve. One, we were already able to see it for M87, and the brightness, as we say, it's like about of the order of 1 millijansky in total flux, and about I think it's about 150 to 200 millijansky the correlated flux. Yeah.
So doesn't a source being brighter help your resolution? Or to ask the question another way, I would kind of naively expect these lines to be oblique rather than vertical.
True. Well, although resolution is more sort of a distance thing, right? But yeah, sure, to make it more precise on oblique lines might be something that you may have to take into account. But there are also other factors like the distance that really goes into estimating the ring size, if it is a luminosity distance or the angular diameter, angular distance, and so on. Yeah, but again, that won't be a major showstopper here. Something that has to be, of course, improved. But like I said, all these sources are still being investigated in terms of their So for example, we already published the results of Centaurus A and 3C279. All the other red sources have already been observed. We are working on it. We expect to have results sometime soon.
A question from Jim Blocky, that's related. For resolved source, is it flux or surface brightness that is the limit?
I'm sorry, let me read here. For resolved source, is it flux or surface? Well, in this case, it is still the flux, I would say, than surface brightness, because at least when we talk of radio or millimeter observations, it's mostly the flux that's the stopping factor than the surface brightness. But again, things have been different at centimeter wavelengths because it depends on if it is dust that's affecting the observations, in which case surface brightness will be one of the factors, or if it is just pure synchrotron emission, then it's going to be the flux. Yeah, again, things that has to be explored. But that's a good point, because these sources, for example, most of the sources that I'm investigating, they are mostly sort of Seyfert galaxies, meaning they are dust enshrouded galaxies. So if given the spectrum, if it's starting to rise as it is for Sagittarius A, then it could be the surface brightness that's one of the factors. But if it is not, if it is sort of flat and mostly synchrotron emission and not thermal synchrotron, sometimes suspected, then it could be just the flux that's of importance that dominates over the surface brightness. Okay. All right, so that's what this figure tells us. It's a takeaway of this figure. More iterations will be done as we get high precision measurements of the mass and the 230 gigahertz flux and so on. So this figure is going to keep iterating over the years. Sorry. Okay, but that's for the EHT. And again, the reason why it's more important for us and all multi-wavelength physicists in EHT and beyond to work together is because although EHT is going to give us all the images and so on, it's equally important to know some of the accretion and jet physics in these sources so that we can enhance our theoretical interpretation. So talking of accretion physics, obviously the best bet is X-ray observations. And of course, everyone would like to start with exploring the iron K alpha line if there is one in the source, which of course can immediately tell us about the the black hole spin, etc. Should the line be coming under the influence of the black hole from the disk, and the line profile can also tell us, this is an important factor also, that tells us about which relativistic physics is the dominating factor depending on the profile, which can already reduce our effort when we try to advance our magnetohydrodynamic simulations, depending on if it is a special relativity or GR or Newtonian, etc., and so on. So that's one of the major things that at least we can take away with accretion physics, something I'm sure we might have known about Mike's works, and that's of course going to be more important in the coming years when there are more high sensitivity missions that are being planned with the expectation of finding more sources with the iron K line. But then talking about jets, we jump to the other end of the spectrum at the radio frequencies, again with VLBI observations, which can probe the structure of the jet, and multi-frequency observations, etc., can tell us about the jet profile, how they are collimated from the base of the jet, and so on. So this figure is basically telling the same. And again, to be of more relevance to the studies here, I picked out one of those interesting cases where they explore mostly the safer galaxies, low luminosity AGNs, which has not as powerful jet as any blazar or radio loud AGN has. So again, improving the sample statistics is very important. That's exactly what we are again doing with VLBI observations. We got plenty and we are currently working on that. So at least what we can immediately take away from this figure is that the collimation is sort of loosely bound in terms of these low luminosity AGNs, which is not surprising because the jet is not very powerful. Again, the reason why we are it gives us an impetus over powerful sources is because at least with EHT, there is a good chance we might be able to resolve more into the accretion flows. And in terms of the theoretical work, it's going to be lesser in terms of incorporating the jet physics into the simulations, which is only going to amplify the workload in terms of all the computation times and so on that one has to factor in if you have to grid the extent of the jet in the simulations, something I'll get to it in a bit. So yeah, talking of multi-frequency observations in jets, it's quite important because due to opacity constraints, the emission region is going to be shifted, called as the coarse shift effect. And sort of extrapolating this effect at multiple frequencies, so one can already sort of trace the base of the jet and maybe also the location of the black hole, etc. This has been done in various about hundreds of radio loud AGNs, blazars, which has excellent sample statistics based on Mojave 15 gigahertz VLBA monitoring. We are trying to start similar observations of low luminosity AGNs, which is again very important, and especially in terms of future observations with all next generation facilities like the VLA coming up, which can also have a higher sensitivity. Doing this is going to get even more easier, but with all the things that we expect for EHT, it's also going to be a necessity in the near future. But at least the information that we have on hand of these low luminosity AGNs is that based on the radio observations is at least the spectral index tells us if the sources are disk dominated or jet dominated. The statistic is really low, so it's not an immediate takeaway, but at least the information that we have based on the millimeter end of the spectrum already tells us if the source can be more disk dominated or not. So using at least source like Sagittarius A, which has been quite extensively studied in literature, not just by us, but by various groups, we extrapolate that information to at least sources what we are studying. And at least the immediate takeaway is that there is a transition region in terms of disk and jet dominated sources. And at least this can help us in weighting the sources, because again, if the interest is more trying to study the photon rings, shadows, accretion flows, etc., we wanted to start more by observing the disk dominated sources over the jets, so on. So we get the observations. Now what we do is, of course, we move to the theory side in order to do the interpretation. The way we do and the way it has been done quite extensively and remarkably well, at least with the EHT for the M87, is in terms of studying the accretion flows by doing all the GRMHT simulations. The concept, at least to put simple terms, you take relativistic physics that you wanted to explore, and you blend that to the fluid mechanics, the magnetohydrodynamics part, the plasma physics part, And then finally, to get your final images, you do the ray tracing of these simulations, which can produce an image at any frequency of interest, be it radio, X-rays, optical, you name it, and at a given resolution, etc. So yeah, so what this, I mean, another way to put this in terms of this nice flow chart is that it's basically the study of energy flow all the way from black hole to jets, different kinds of energies that are dissipated along the way, with magnetic fields playing, of course, an important role in terms of collimating the flow. This is going to be an interesting thing to explore the magnetic field, because at least in the radio end of the spectrum, only with powerful sources, powerful quasars, you see polarization signatures. For example, again, the second set of papers that we released for M87, we studied the polarization. But at least for those sources which we are immediately interested in, the ngEHT, the ones that we are seeing now, it's going to be really challenging, because we don't even have a powerful jet as M87, meaning detecting the polarization is going to be sort of impossible with the existing array. But again, we never know how it goes, if there is a variability or if there is some instability that helps us see the magnetic fields is going to be impressive. But then, of course, on a large scale, you got the radiation outflows, could be in terms of the jets or the winds, etc., which is again, some of us radio folks, we study that using VLBI observations to study the jets, but spectroscopists, they study the outflows in terms of the molecular outflows and ionized outflows, etc., which are equally important, because at least the thing that we are trying to do here is that since some of these sources being more dusty and star forming, etc., you're going to see more of these spectral lines. So trying to relate those the collimation regions from the outflows, from the molecular and ionized outflows, to the location and launching of the jet can be itself an interesting, important study, because then it will make it all the more easier to study the polar axis of the black hole and where the black hole jet is launched, etc., which is again a factor that's more important for simulations. So not to confuse you too much, just to show an equation here about geometry simulations, what we try to solve here. One of the key factors about geometry simulation is that it is mass invariant, so you can scale the black holes to any mass of your interest. So that's itself is one of the major advantage of geometry simulations. Of course, spin is something that has to be quite robustly tested for different kinds of species of electrons physics that goes into the simulations. But then the next part, of course, is to do ray tracing of these simulations. So with all the plasma physics and magnetodynamics that goes into making the geometry simulations, you use that as a seed to trace the photon trajectories, taking the, again, GR into account. And all you do is basically see how the space-time curvature works, at least in the immediate regions of the black hole, in order to generate images that at least looks more identical to what we expect from the photon orbits of the black holes, etc. So it's a simple, straightforward integration. I mean, although the equation might sound a bit fancy, it's not as complicated as how geometry simulation is, because I would say 90–95% of the complication is taken care of the geometry stuff. The ray tracing is pretty straightforward. It's just about integrating the photon orbits, the trajectories, and just solving for the radiative transfer equations, which then can provide us a suite of images, again, depending on your seed simulations. And these, when sort of convolved with your observing beam, again, whatever frequency, whatever instrument you are using, they can be directly compared with your observations, which is exactly what we did for M87. So that is one way of doing it. Then the other way, at least leaving out just focusing on one frequency, but expanding across the spectrum, is looking at the broadband SEB. But of course, care should be taken that you take high resolution measurements here, because like I said, if the source has a powerful jet, and if you're going to take a large field of view, then it's going to be almost impossible to apply the GR physics, at least with the existing models, because one need to train a lot of simulations before you have a really large scale field of view physics into your hand before you apply that to your SCDs. So at least if you wanted to study the accretion flows, we try to get high resolution measurements. At least this is one of the cases where Sagittarius A was studied in literature. And what then happens is, again, you test the two different famous accretion models, the magnetic field, the MAD model, and the standard accretion and normal evolution models. Again, based on your GRMNG simulations and the ray tracing, you can test your theory and try to get a best fit or whatever constraint that we have to understand all the again the accretion physics that goes into making this source. What can also do in order to have a much more robust constraint is to simultaneously study the light curves, the variability shown by these sources, again taking the resolution into account, because at least when you have the when you're done with one set of simulations and when you have the ray tracing tool on hand, you can sort of extend it to any branch of spectrum or any kind of light curves, images, etc. That is straightforward. So in order to improve the constraints, it's equally important to study them on light curves. Of course, unlike the SCDs, one can't apply directly to the light curve, so you might have to think of working on the Fourier space or something. These are things that are still being explored, but something that will be implemented in the near future in order to get much more high precision understanding of the accretion physics in play. Again, this is just a quick preview of the EHT result, the way it was done for M87. Is that at least the EHT observables are actually shown here. We got the amplitudes across different combinations. The baselines of telescopes are what you see on top. And the closure relations, what I said, the combination with three set of antennas and the phases, they tell you, because since phase is going to tell you the structure, underlying structure, and since different structure is going to be probed by different scales because of the different combinations of antennas in the array. But since we have an image, we have the observing beam into account. We can smear that on the image, and then we can immediately test that right over the observations to see, again, get an understanding of the best fitting model. And depending on which one fits, we can try to at least agree upon the final physics that goes into making that image. This has also been done quite extensively for M87. There's also another important thing here is to know the understanding of electron distribution function, which is again an important factor in the accretion flows. But again, trying to study this across multiple frequencies, across multiple set of images with these simulations is sort of important. So this work studied that quite extensively, and probably one of the first set of such works, which probably is going to spawn more works in the near future. Yeah, I'm going to skip that. But yeah, so just a quick thing of what we did for the low luminosity AGNs as a start is to work already with these high resolution measurements of their series, looking at which accretion models, either the ones by the dominated by the magnetic fields or not, for a different range of spin values. We tried to fit them. At least the immediate takeaway is that the magnetic field seems to be better behaved, although in terms of a best fitting one, the one without that seems to be a better approximation. But again, as you can see, but one of the major reasons why Mike and I are trying to get these hard X-ray observations from New Star is we wanted to probe this channel where there is still missing information for quite a lot of these sources, which can again constrain these models better, and then we can have a better understanding of the accretion physics, etc. So putting all this together sort of as a roadmap is a lot of work has to be done, and of course we are doing it in EHT, but this is not only EHT observations. In fact, before we go into EHT, we need to have a multiwavelength understanding of these sources, be it X-rays, optical, etc. I mean, optical observations are going to be useful, especially if we can have the IFU observations using Gemini, Keck, or VLT, etc., or with a JWST. We can do dynamical studies and try to get their black hole masses, which is again important. But then VLBI observations are going to be important to tell us more about their radio jet, if there is one, and how compact it is, etc. X-ray, without a doubt, accretion, and I don't know if it is going to be more synchrotron dominated than the X-ray, etc., depending on the source under study. But yeah, one of course needs to put the picture in a much broader perspective, the broadband SED, and also try to expand all the theoretical studies that are being done by various groups, even outside EHT, and try to put them together and improve the understanding, etc. So it's a long process. What we did in EHT at least is a mere scratch on the surface, and of course, as some of you might have known, we are establishing sort of a next generation EHT, sort of opening up more to the community, because obviously this is something that should be more available for people even outside the consortium. But it's a process that's going to also take a while, because we ourselves are still refining several of our calibration codes that goes into analyzing the data and etc. But yeah, please feel free to reach out to us anytime if you are interested, and also to me directly if you have any important questions about EHT in general. If you have any of your favorite targets that you would like to observe, or at least would you like to know more, just happy to discuss anytime. So yeah, thank you so much.
We have time for a few questions before people start disappearing. So there's from Buckley wanted to know about a little bit more about polarization.
Yeah, I mean, I'm just wondering.
We have the image of M87 that's been shown in polarization. What are the other prospects for seeing polarization at the base of jets and other sources?
So 3C279, which we again published, is we are going to clearly see some polarization. It's one of the obvious candidates for polarization, even beyond M87. Again, something that we are going to we're going to publish coming months or something. There are various other radio loud AGNs, blazars, which we have observed. At least in millimeter at our frequencies, Some of them are not very obvious as what it has been in low frequencies. So they are still going to be a challenge for us with the EHT to detect in at least as many sources as we saw in low frequencies. But we certainly believe that there are a few which are obvious candidates. Maybe we can even see circular polarization in 3C279, which has already been published at low frequencies. So yeah, that would be like, again, quite a significant finding. But yeah, we'll probably say that in coming months or something. We'll keep you posted. Yeah. Anything else?
So for the low luminosity AGNs that you showed on your previous slide, the data points that you showed on that SCD,
Yeah.
these are, so yeah, so what instruments are these?
Okay, so what I tried to do here is, of course, one can say that there could be broad range of data in literature or net or whatever, but I felt like it's, at least when we try to do all these accretion physics, it's more important to get a quasi-contemporaneous observations to ensure that the variability doesn't play an important factor here there. Hence the paucity of the data. But so at least the radio fluxes are from VLBI measurements, and I think these are from optical are from HST and VLT. Again, I try to be very careful in how I choose the sources and what measurements goes into that. Again, if the whatever band it is, if there is some sort of a resolution problem, again, try to be quite wary about that. X-rays, I think they are from Chandra and so on. I didn't do much of reduction. I just took available fluxes. But then I think this includes perhaps less than a dozen sources, about 10 sources maybe. And all I did was take a geometric mean at a given frequency, at least to get a handle of the error bars. That's all. But this is just a start, and I just feel like at least trying to get this is going to be a challenge in trying to get sort of a contemporaneous observations for a lot of sources. But that's something that has to be done. Than trying to get observations around the year might be something more loosely constrained, because although these sources may not vary as much in the radio and maybe not much in optical, but there is a variability at least at one other frequency. So if the interest is at least here being more trying to get a handle of the accretion physics and so on, then this is something probably we would like to do. I was
gonna say, so these are beamed objects. So you are at least you think you're looking at the jet rather than the disk. Is that true or not?
No, we feel that we are here looking at more of the disk dominated sources, because at least I picked sources that are more along those lines. I know the SCD might tell us more, at least with the synchrotron peak here. That's again why like the infrared part of spectrum probably needs to be better sampled. I know like at least when we do the Blazar SCDs, at least the spectrum might be more telling us more about the I mean how jets probably dominates. But here it's I think we believe it's more the disk.
So then the model lines are, so they show kind of a synchrotron spectrum that goes through the radio, and then the thermal emission from the disk. Is that what the models are?
Well, so it's not like the leptonic models and the hadronic models, for example, what we do, because that's also something I used to be doing. I'm still doing that for Planck AGNs. But here, these are purely the ray traced spectrums that we got out of the accretion flows. Just assuming, for example, let's say, for example, there are these 3 different categories of accretion flows. Although in this case, we have some jet. But at least the ones which we tested on those spectrum, we didn't have any jets. We, of course, had an inclination angle for a jet as one of the parameters, but we didn't assume that the jet was a dominant factor there. Something again we are going to implement now, because so far whenever JETS has been there until probably now, it's mostly has been relativistic MHD. GR MHD has been is a complication, as again things you might have known. Because again, one needs to be very careful on what sort of a coordinate system you take into account and so on. So that has to be done without a doubt, and we are starting to do that. So at least when we try to generate the spectrum, that all the lines that you see here, we just assume it's more the disk that dominates here. Yeah. Again, hence the reason of handpicking the sources, making sure that there is no contamination from the jets and these sorts of things.
Maybe, Jim, do you want any last question there? You want? He's got a few questions in the chat.
Can you hear me?
Yes.
Oh, okay. I thought maybe you couldn't hear me. No, I was just wondering, like, as part of a multi-wavelength campaign, so if the EHT is up and running, then one leg of it, like ALMA or something, is up and running. That could maybe give the temporal coverage for like millimeter kind of accretion phenomena, which then might be correlated, and it would be very fascinating to see how that correlates with the synchrotron self-Compton, so, or inverse Compton, sorry, with the synchrotron inverse Compton.
Yes. Very important point indeed, which is why the way at least we are trying to, so Jim is just asking about studying the variability, the temporal aspect of the accretion flows, obviously extending our understanding of the, at least in M87 and Sagittarius in the future. So at least in EHT, of course, we wanted to do that, which is why one of the near future efforts that we are planning is we are trying to go into agile observations, at least when we can monitor, because one of the major constraints with EHT is the reason why you could have seen that we have always observed at around March, April is this was the best observing time when it comes to weather-wise across all stations. Some stations might have better observing conditions at a much later time, etc. But put together, this is the best time in the year when we can do it. Of course, to start things off, we did like we had just 1 week or 2 weeks observing window when we picked those days when the conditions was good, etc. But of course, with having already been successful with the M87 results and with various other groups also being converging onto our same result, now it's of course all the more important that we study the accretion flows. So of course, studying the accretion flows depending on what time scale you are important. And for example, M87 time scale, you might have to sample it over 2 weeks or something. Or for a non-spinning black hole, like the case of a Sagittarius A, the photon orbit might be like about 60 seconds or 200 seconds be spinning or non-spinning. But if you are looking more sort of an ISCO time scale, much larger much larger scales, then you might be looking at out of a few hours or something. So yes, it's something we are trying to commission in the coming years. There are several challenges, of course, but that's without a doubt that we are trying to do. At least with having already had several successful sort of contemporaneous X-ray observations to sample the inverse Compton or the Compton scattering, we really have the motivation to do that.
I'm just kind of thinking, you said that things were correlated. I mean, you've brought magic into the collaboration. Magic and Veritas in the old, in the old days it was Hegra and Whipple, but the longitudinal separation can also be good if you're looking for very short time scales. So, and the nice thing is that March-April timescale, when EHT, Northern Hemisphere instrument, can look, that overlaps very nicely with when Veritas would be looking at things like Mercurian 501 and stuff anyway. So I assume, maybe Manel can say something, but I assume and hope that our Veritas instrument is slaved to your observations, but we'll see.
Right.
What do you think, Manel? Are people planning on this or?
Did you hear? Okay. Okay. So yeah, no worries. Jim was asking about keeping Veritas and Magic, for example, in the loop, and since Veritas was, I mean, we had anyway them observing part of the EHT multiwavelength campaign. So at least Jim was trying to make a point that Veritas is trying to, at least in terms of these temporal coverage and so on, if the plans are to do something or keep pursuing this more, push more into the near future and so on.
I think we have sort of an agreement with EHT, with Veritas. I think so far only for MAD South.
Right.
So this is the only object that we have been
Right.
observing at the same time as EHT.
Right.
There might be, I forget all the sources of what in red, but there might be a couple more on that plot that we showed. There might be a couple more where it would make sense for us to look, like OJ287 sometimes we've seen it, and 3C279 has been seen too. And SENA
Yeah, I
has
was about
seen
to
it
say
in the
that.
south. Yeah, this would be in the south, it would only be has.
Yeah.
Veritas cannot see it.
Hess will be seeing that. Yeah.
Yeah, NGC 1275 we've
Yeah.
also seen.
I'm really excited about Markarian 501 because we know this is one of these rare sources where, I mean, you know, Henrik and I were involved in the very early days of this. You can actually resolve the variability in the TEV, and it's a great source where you can really see it going up and down, and maybe even do spectral variability. And it's there on the other side of your vertical line. So I think, Manel, I think that's an urgent one.
Yeah. Talking about Markarian 501 and so on. In fact, yeah, probably after the talk, I'll just discuss with Manel, because we are going to observe 501 this time. So I don't know if anyone has reached out to you or not, but it will be without a doubt interesting, because I mean, having been part of Finnish group, and also since we team up with Veritas, when I did the observations, I remember Markarian 501 being one of the prime suspects of Veritas observations. So yeah, it would be interesting, and yeah, maybe I should explore more in terms of black hole masses, TeV sources, and how it can fall into when it comes to EHT observations and so on.
Yeah, we can talk later.
Yeah, sure. Thanks, Jim.
Okay, let's
Thank you.
stop there and thank Becky again for a great talk. See you guys next time.
Thank you, everyone.